Thanks for having me. It's very exciting to hear about all the capabilities of the pressurized rover. I'm Craig Hardgrove. I'm a professor at ASU, Arizona State University. I've been a participating scientist on the Mars Science Laboratory Curiosity rover for the past 10 years or so. And we're also sending a neutron and gamma ray detector to the Gruithuis domes on the Lunar VISE mission in 2028. And I was the PI of the LunaMap mission, which launched on SLS. So have some experience working with these types of instruments, these nuclear instruments on planetary surfaces, and I wanted to use this time to really show some of the value of active nuclear instrumentation on planetary surfaces, speaking directly from our experience on the Curiosity rover. And this instrument, there are several different instruments out there that are capable of this. This is one that we've proposed to a few different NASA opportunities, and fingers crossed we hear something back positive, but we'll keep trying. But this is something that flew on the Curiosity rover, and I'll show you some data of the really great things that you can do with it. And we hope we can uh, send one soon. So if you go to the next slide. Deborah mentioned earlier some of the science goals around water on the moon. The map on the right was made with Lunar Prospector's neutron detector, and it shows the distribution of enrichments of water ice throughout the south pole of the moon. For reference, the spatial scale is on the order of 50 square kilometers per pixel. So, the poles are enriched in hydration, but with that spatial resolution, we really weren't able to tell whether the enrichments of hydration were confined only to the regions of permanent shadow, or if they might extend outward into illuminated regions or partially illuminated regions, which is something that we might expect if these volatiles have been redistributed by impacts and buried subsequently. So it's something that we really would like to investigate with a rover on the surface so that we can understand how the hydration of the lunar surface varies along a traverse and with different surface conditions. And the image on the left just shows the permanently shadowed regions throughout the South Pole are labeled in red, and then in blue you can see areas where there's been identifications of surface frost. And just to give you a sense, not all permanently shadowed regions are created equal. Some have been shown to hold frost and some do not. If you go to the next slide, be able to see some other data. So we have additional neutron data from orbit from Lunar Reconnaissance Orbiter and the LEND instrument. You're also able to play some tricks with the Lunar Prospector data, which is shown in the middle, where you can reproject it, assuming that all of the signal that we saw from hydration is contained within the permanently shadowed craters. And you can also look at maps of ice stability, and for some reason it's not projecting correctly, but probably familiar with the regions of ice stability that have been identified from thermal imaging and thermal data from orbit. And those have showed that in some areas we would expect that there could be ices stable at the surface, but in other areas throughout the South Pole that are illuminated, we would expect there to be volatiles that are preserved maybe 10 to 20 centimeters below the surface. So there is some expectation, but that we would see volatiles below the surface, as well as some inconsistencies between all of the data sets that we've collected. So I think there's some open questions, like Deborah mentioned, about what is the actual abundance and what is the distribution laterally, as well as into the subsurface. And I'll talk a little bit more about that in a minute. Go to the next slide. I think the previous speaker, Teruaki, showed or discussed this really well, so I don't need to go into it, but there are different ways of detecting neutrons in planetary science. This just shows a diagram on the left of all the different nuclear interactions that can occur from the galactic cosmic rays. But I just want to point out here that primarily when we measure the thermal and epithermal, meaning sort of the lower end of the neutron energy spectrum, we're primarily sensitive to the macroscopic energy loss cross-section as well as the macroscopic absorption cross-section. That really is referring to how much energy did the neutrons lose with collisions with light elements, primarily hydrogen. And the absorption cross-section is dominated by elements that have a particular property of their nucleus that makes them absorb low-energy neutrons and emit a gamma ray. And so those elements on the surface of the moon can be gadolinium, samarium, europium. There have been papers about that. We also see on Mars enrichments of iron can do the same thing. So if you go to the next slide. We just did some simple modeling of compositions that have been detected. So there have been, if you're familiar with L-Cross, it detected a significant amount of mercury actually in the plume that was ejected from the impact. It's about 1.28%. And if you look at typical compositions at the South Pole of the Moon and put some mercury in the composition that was observed from L-Cross, you see that it really makes a significant impact in the neutron absorption cross-section. If you go to the next slide. This is showing how we interpret the thermal and epithermal neutron data from a passive experiment. All those points that you see on the plot on the right represent the measured values. These are simulated, but these would be the values that you measure with two sensors that measure thermal and epithermal neutrons. And you can see that there's a lot of degeneracy here. We're only modeling 3 different hydrogen contents that are at depth. And we're allowing all of the other parameters to vary. So the neutron absorption cross-section can vary in the top layer as well as the bottom layer, as well as the depth of the top layer. These are all things that geologically you can come up with plausible explanations for. And you can see this is very difficult to come up with a unique solution. If you go to the next slide. This is just showing a subset of those. So this is when you fix certain parameters. In this case, we're fixing for both of these two families, the families of curves on the left and the right. We have different thermal neutron absorption cross sections in both the top and the bottom layer. And so if you just look at the family of curves on the right, that's showing what Teruaki was showing, where you have this sort of diagram that shows here's all the parameters that you could measure the thermal and epithermal neutron count rates and how they vary with increasing hydrogen, increasing burial depth of that hydrogen. And if you look at the dashed line that I drew on the right side, that shows if you just introduce that high thermal neutron absorption cross-section material into a thin layer at the top, you can see that we would get confused if we just had thermal and epithermal neutron count rates with something that's just a hydrated material that's buried at depth with a dry material at the top. So we really need some way to untangle what the composition of both of these layers is. And if you go to the next slide, we've demonstrated that you can do that on the Curiosity rover. So by doing that, you use a timing technique. So you bring the neutrons with you, it's called a pulse neutron generator. You accelerate deuterium atoms into tritium atoms, and you create 14.1 MeV neutrons, and those are emitted isotropically, but many of them go into the lunar surface and they interact. And you look at the top graph there as showing the time profile of arrivals of the lowest energy component of the neutrons. And by looking at the shape of that time profile of arrivals, we can say how deeply buried the hydrogen is, as well as how many neutron absorbers there are in the subsurface. If you go to the next slide. This is showing what it looks like for each of the thermal neutron diaway curves as you increase hydration in elements of 0.1 weight percent hydrogen, just showing it goes up uniformly. If you go to the next slide, these are simulations. This is showing this is a Markov chain Monte Carlo analysis. So you go hit to the next slide, I guess it's animated. Just showing how the thermal neutron diaway curves vary with increasing water, as well as increasing thermal neutron absorption cross-section. And you can use a technique, this Markov chain Monte Carlo, to disentangle the covariance between all of these parameters. So in this case, we're modeling water equivalent hydrogen and the burial depth. And you can see that we get a pretty nice, well correlated solution here where we have a nice solution for the water equivalent hydrogen as well as the depth. If you go to the next slide, because we have so many parameters to work with in terms of the thermal neutron diaway, we get a count rate in every time bin after the pulse. You can vary many parameters in the subsurface. So in this case, we're varying 5 parameters in the subsurface, the bottom and top water, as well as the bottom and top thermal neutron absorption cross-section, as well as the depth. And in some cases, we do a great job of constraining it. Like you can see in the bottom water and the top water, we have a nice distribution where we can calculate a mean. We also can calculate the bottom thermal neutron cross-section, but in some other cases, we don't get a nice probability distribution and we can't say it. That's just an honest way of interpreting. There's a lot of degeneracy in some of the variables for some of the data, but you could imagine that when we only have a couple count rates, the degeneracy is significantly worse. So we're really able to say how deeply buried this material is and what the composition of both layers is with this technique. If you go to the next slide. This is showing some lunar examples. So these are simulations of an instrument that we proposed and the capabilities to detect increasing amounts of hydration all the way down to 100 micrograms per gram, as well as different burial depths of that hydration and varying compositions. You can see that I'm not going to go through it all, but you can see the increases in the thermal neutron peak as well as the shifts in the timing are really what allow us to untangle all of these different variables in the subsurface. If you go to the next slide. This is the Curiosity rover with the DAN instrument on the back. If you go to the next slide, you just see the pulse neutron generator, I believe. If you go to the next slide, this is showing all of the data. So the Curiosity rover is driven about 13 kilometers across the surface. So really, we're benefiting from having this large data set that we've collected, just like we would hope to get on something like the Pressurized rover. If you go to the next slide. This is showing that we were able to detect with the neutron detector increasing hydration as we drove into the clay unit. You can go to the next slide. This is showing how we got fooled, I believe, by the passive count rates. So this is an area that had, we thought were high hydration at this bright tone material. If you go to the next slide. This is showing an overhead map of the thermal neutron count rates. The red is showing where it really lit up in the thermal neutrons, which would potentially indicate high hydration. But when we went back and looked at it with the active neutron measurement, if you go to the next slide, we're actually able to see that it's low hydration, but a very, very low cross-section buried about 10 to 20 centimeters below the surface. We were actually able to make a map of that as we drove around. If you go to the next slide. We drove, I got the next one. We drove around the area that's shown on the left there. If you go to the next one. Next one. Yeah, so you can see below the subsurface, we were able to map it, just showing that yellow area. It's a layer that's pretty thick beneath the surface, and we were able to show the extent of that. One more slide, just showing that because this is radiation and it is emitting radiation, we just wanted to show that we only get about, once you're a meter away from the PNG, we're looking at 1 millirem per hour. Right up close, it's 4.5 millirems per hour. So not something you want to be standing next to for a long period of time. But because we're pulsing the generator, it's not a high dose. So we're talking, pretty low dose, and it should be safe for electronics nearby. And obviously this would be used when it's uncrewed. That's what we're talking about here. So next slide, I think that's it, probably. Yeah, just talking about how we can identify the hydration as well as the burial depth and discriminate between some of these really important geologically relevant elements that might be contained in the volatiles. I think that's all I have. Sorry for running a couple minutes over.